Hi guys, I'm Mike
I'm X.
and we are
Just
just
two
two
guys.
guys.
Okay, so obviously, right now we're doing a video.
Uh, I'm gonna post this on the YouTube channel too.
Yeah. So this is our first video um,
Podcast,
podcast. Mike does not have a
webcam.
webcam, so he's not going
I've
to be videoing, but we still
I've
wanted to
made
do the video podcast.
I've made up for it by deciding we're gonna review this video.
Yeah.
So
So Mike has seen this before. I have not. So it's something strange that happens when you follow Einstein's math. And
it's a Veritasium video. You should go check out his YouTube channel. He's really good and cool.
yeah,
Um,
so
all right, let's jump into it.
mhm.
You ready? All right.
You can never see anything enter a black hole. Imagine you trap your nemesis in a rocket ship and blast him off towards a black hole. He looks back at you, shaking his fist at a constant rate. As he zooms in, gravity gets stronger, so you'd expect him to speed up. But that is not what you see. Instead, the rocket ship appears to be slowing down. Not only that, he also appears to be shaking his fist slower and slower. That's because, from your perspective, his time is slowing down. At the very instant when he should cross the event horizon, the point beyond which not even light can escape, he and his rocket ship do not disappear. Instead, they seem to stop, frozen in time.
I think that's really interesting
Yeah,
because usually it'd be like, oh yeah, they just disappear, but they freeze in time. What's your thoughts?
yeah. I honestly did not expect that, and also I thought like a black hole. Like originally, before we started seeing this video, I thought a black hole was more like a storm that just kind of sucks stuff in, and like in the eye of the storm, it's like calm. But like that's actually really interesting how it like stops
Yeah.
time.
I mean, it's not really like, well, it doesn't really stop time. You'll see later in the video, but it's not really like this calm. There's an accretion disk around it, which is just a cloud of dust around it. So you're right. It's kind of like the eye of a storm, except it's just like a round ball that spins and it black ball and it just sucks in and it goes straight to the singularity.
Yeah, it will be interesting to see like if he explains like what happens if you like if there's like a lot of stuff that gets into a black hole and all that.
Yeah. If you go into a black hole, I think it's really funny the term for it. What happens to your body is it gets stretched out, and it's called spaghettification.
Oh really?
Yeah. All right. Uh, just want to make sure again, this is Veritasium. I'm not trying to copy or steal or claim any of this work as my own or our own. This is Veritasium on YouTube. Will put I'll put a link in the description for his YouTube channel.
Yeah, not trying to get
The
copyrighted.
light from the spaceship gets dimmer and redder until it completely fades from view. This is how any object would look crossing the event horizon. Light is still coming from the point where he crossed, it's just too redshifted to see. But if you could see that light, then in theory you would see everything that has ever fallen into the black hole frozen on its horizon, including the star that formed it. But in practice, photons are emitted at discrete intervals, so there will be a last photon emitted outside the horizon, and therefore these images will fade after some time. This is just one of the strange results that comes out of the general theory of relativity, our current best theory of gravity. The first solution of Einstein's equations predicted not only black holes, but also their opposite, white holes. It also implied the existence of parallel universes and even possibly a way to travel between them. This is a video about the real science of black holes, white holes, and wormholes.
Eric, can you pause it real quick?
Ah,
All right, can you just pause it real quick?
yeah. What?
All right. So I was thinking it would be insane if we could actually travel through universes, like parallel universes. Like,
Yeah,
what would,
he actually describes a way how to do it theoretically.
yeah. What are your thoughts on, like, what would a parallel universe be like?
Um, a parallel universe. Okay, it's either completely different, nothing like it, or it's like that one theory where it's like every decision you make creates another timeline in another universe where you made the other decision or different decision. You know, it's
Yeah.
either like that or it's like completely different. I personally don't know because I don't think I'm smart enough to have any of those like theories or thoughts. I'm just saying,
Yeah.
yeah.
Yeah, that would be really interesting to, like, see what life would be like if you had made, like, one different decision.
Yeah. And like it could change the whole entire course of your life.
Yeah.
Alright, you ready?
Yeah.
The general theory of relativity arose at least in part due to a fundamental flaw in Newtonian gravity. In the 1600s, Isaac Newton contemplated how an apple falls to the ground, how the moon orbits the Earth and Earth orbits the sun, and he concluded that every object with mass must attract every other. But Newton was troubled by his own theory. How could masses separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it. One man who definitely had a competent faculty of thinking was Albert Einstein, and over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly. Instead, a mass like the sun curves the spacetime in its immediate vicinity. This then curves the spacetime around it, and so on all the way to the Earth. So the Earth orbits the sun because the spacetime Earth is passing through is curved.
Masses are affected by the local curvature of spacetime, so no action at a distance is required. Mathematically, this is described by Einstein's field equations.
Can you write down the Einstein field equation?
This was the result of Einstein's decade of hard work after special relativity. And essentially what we've got in the field equations, on one side it says, tell me about the distribution of matter and energy. The other side tells you what the result.
I think it's crazy that like just these random symbols and stuff can tell you so much.
Yeah. Like, yeah, it's just insane. Like, what such, like, such big things could be described in such little words or equations.
Math is so confusing.
Yeah. Like, when did we get big R, little a, little b?
Whatever that is.
Yeah.
Is that an omega? I can't tell.
It looks like a sideways omega.
Yeah.
For those of you that don't know, an omega is a Greek letter in the alphabet.
Yeah.
Resultant curvature of space-time is from that distribution of matter and energy. And it's a single line. It looks like, oh, this is a simple equation, right? But it's not really one equation. It's a family of equations. And to make life more difficult, they are coupled equations, so they depend upon each other. And they are differential equations. So it means that there are integrals that have to be done, da, da, da. So there's a whole bunch of steps that you need to do to solve the field equations.
To see what a solution to these equations would look like, we need a tool to understand spacetime.
So imagine you're floating around in empty space. A flash of light goes off above your head and spreads out in all directions. Now, your entire future, anything that can and will ever happen to you, will occur within this bubble, because the only way to get out of it would be to travel faster than light. In 2 dimensions, this bubble is just a growing circle. If we allow time to run up the screen and take snapshots at regular intervals, then this light bubble traces out a cone, your future light cone. By convention, the axes are scaled so that light rays always travel at 45 degrees. This cone reveals the only region of spacetime that you can ever hope to explore and influence. Now imagine that instead of a flash of light above your head, those photons were actually traveling in from all corners of the universe, and they met at that instant and then continued traveling on in their separate directions. Well, in that case, then into the past, these photons also reveal a light cone, your past light cone. Only events that happened inside this cone could have affected you up to the present moment. We can simplify this diagram even further by plotting just one spatial and one time dimension. This is the space-time diagram of empty space. If you want to measure how far apart two events are in spacetime, you use something called the space-time interval. The interval squared is equal to minus dt squared plus dx squared. Since spacetime is flat, the geometry is the same everywhere, and so this formula holds throughout the entire diagram, which makes it really easy to measure the separation between any two events. But around a mass, spacetime is curved, and therefore you need to modify the equation to take into account the geometry.
This is what solutions to Einstein's equations are like. They tell you how spacetime curves and how to measure the separation between two events in that curved geometry.
Einstein published his equations in 1915 during the First World War, but he couldn't find an exact solution. Luckily, a copy of his paper made its way to the Eastern Front, where Germany was fighting Russia. Stationed there was one of the best astrophysicists of the time, Karl Schwarzschild. Despite being 41 years old, he had volunteered to calculate artillery trajectories for the German army.
At least until a greater challenge caught his attention: how to solve Einstein's field equations.
Schwarzschild did the standard physicist thing and imagined the simplest possible scenario: an eternal static universe with nothing in it except a single spherically symmetric point mass. This mass was electrically neutral and not rotating. Since this was the only feature of his universe, he measured everything using spherical coordinates relative to the center of this mass. So r is the radius, and theta and phi give the angles. For his time coordinate, he chose time as being measured by someone far away from the mass, where spacetime is essentially flat. Using this approach, Schwarzschild found the first non-trivial solution to Einstein's equations, which nowadays we write like this. This Schwarzschild metric describes how spacetime curves outside of the mass. It's pretty simple and makes intuitive sense. Far away from the mass, spacetime is nearly flat, but as you get closer and closer to it, spacetime becomes more and more curved, it attracts objects in, and time runs slower. Schwarzschild.
That's pretty cool.
Yeah, like, how can, like, one thing control, like, so many things around it? It's, like, insane.
Yeah.
Or, like, even the ripple effect, it's kind of like that. Like,
Yeah.
one thing controls another thing, which controls another thing. Like, for instance, the sun controls the earth, which controls the moon, and, like, so on and so on. It's just insane, like, how one thing can control so many things.
It's just a chain. And
Yeah.
then, like, if one thing's gone, if the sun's gone, then nothing else works.
Mm-hmm.
Then the Earth would just be drifting within it.
Yeah.
Sent his solution to Einstein, concluding with, "The war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Einstein replied, "I have read your paper with the utmost interest. I had not expected that one could formulate the exact solution to the problem in such a simple way." But what seemed at first quite simple soon became more complicated. Shortly after Schwarzschild's solution was published, people noticed two problem spots. At the center of the mass, at r equals 0, this term is divided by 0, so it blows up to infinity, and therefore this equation breaks down and it can no longer describe what's physically happening. This is what's called a singularity. Maybe that point could be excused because it's in the middle of the mass, but there's another problem spot outside of it. At a special distance from the center, known as the Schwarzschild radius, this term blows up. So there is a second singularity. What is
Can you
going
pause it
on
real quick?
here?
Yeah.
All right, so that right there, right next to the second to last like letter slash digit is the omega that we were talking about earlier.
Yeah, this
And
is the
like,
omega.
how did that get into like math and
Yeah,
science?
like who thought of that?
Uh huh. Like
And
it's
like,
one thing to put like algebra, but it's a whole nother thing to put like different types of algebra and even different languages into math.
yeah, like at this point, math isn't numbers anymore. There's like 3 numbers in this entire equation besides the exponents.
Yeah,
Yeah.
math is just like so complicated.
Yeah. You ready?
Yeah.
Well, at the Schwarzschild radius, the spacetime curvature becomes so steep that the escape velocity, the speed that anything would need to leave there, is the speed of light. And that would mean that inside the Schwarzschild radius, nothing, not even light, would be able to escape. So you'd have this dark object that swallows up matter and light, a black hole, if you will.
See, that's the accretion disk. That actually doesn't go above the black hole. It warps light so that like behind the accretion disk actually appears above and behind it. Like
Yeah.
it's just a ring. It doesn't actually go up.
Bro, it's insane how like an error in the problem turns out to be like a huge theory that
Yeah.
is like
Actually,
well known
we
today.
yeah, we got our first picture of a black hole just a little bit ago.
Oh yeah, when did we do that? Do you know?
I don't know. I think it was like 2019 or 2020 something maybe.
Oh, well that's crazy.
Yeah.
But most scientists doubted that such an object could exist because it would require a lot of mass to collapse down into a tiny space.
How could that possibly ever happen? Astronomers at the time were studying what happens at the end of a star's life. During its lifetime, the inward force of gravity is balanced by the outward radiation pressure created by the energy released through nuclear fusion. But when the fuel runs out, the radiation pressure drops, so gravity pulls all the star material inwards. But how far? Most astronomers believed some physical process would hold it up. And in 1926, Ralph Fowler came up with a possible mechanism. Pauli's exclusion principle states that fermions, like electrons, cannot occupy the same state. So as matter gets pushed closer and closer together, the electrons each occupy their own tiny volumes. But Heisenberg's uncertainty principle says that you can't know the position and momentum of a particle with absolute certainty. So as the particles become more and more constrained in space, the uncertainty in their momentum, and hence their velocity, must go up.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But
So the more a star is compressed, the faster electrons will wiggle around, and that creates an outward pressure. This electron degeneracy pressure would prevent the star from collapsing completely. Instead, it would form a white dwarf with a density much higher than a normal star.
Okay. That's insane. And like a singularity gets smaller than that, and it'll have so much more mass than that.
Mm-hmm. Like weight itself is just crazy.
Yeah.
Like even muscle compared to fat. Like how is muscle heavier than fat? I get it's like more dense, but like there could be like someone that like looks like they're 200 pounds, and then there could be someone that looks like they're 160, and then the 160 guy is actually like 210, and the 200-pound guy is actually like 160.
Yeah. All right, you ready?
Yeah.
In a normal star. And remarkably enough, astronomers had observed stars that fit this description. One of them was Sirius B. But the relief from this discovery was short-lived. 4 years later, 19-year-old Subramanian Chandrasekhar traveled by boat to England to study with Fowler and Arthur Eddington, one of the most revered scientists of the time. During his voyage, Chandrasekhar realized that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That means this effect can only support stars up to a certain mass, the Chandrasekhar limit. Beyond this, Chandrasekhar believed not even electron degeneracy pressure could prevent a star from collapsing. But
Can you
Eddington
pause that
was
real quick?
not impressed.
That's crazy. He figured that out at 19 years old.
Yeah.
Like,
On a boat.
yeah, on a boat. And he was just like, oh, I just figured this huge thing out. I wonder, like, how scientists reacted to, like, figuring stuff out. Were they like, oh my gosh, I just figured this out? Or were they like, nice,
Yeah. And like,
thumbs up?
you guys are probably like, oh, well, he probably used some sort of thing to figure it out. They basically have no technology then. Like, just, he's sailing on a ship. Okay?
Yeah.
And he has, like, a paper and a quill, and that's basically it. Probably like a mini cheap telescope or something.
It's
Yeah.
crazy.
He publicly blasted Chandrasekhar, saying, "There should be a law of nature to prevent a star from behaving in this absurd way."
And indeed, scientists did discover a way that stars heavier than the Chandrasekhar limit could support themselves.
When a star collapses beyond a white dwarf, electrons and protons fuse together to form neutrinos and neutrons. These neutrons are also fermions, but with nearly 2,000 times the mass of an electron, their degeneracy pressure is even stronger. So this is what holds up neutron stars.
There was this conviction among scientists that even if we didn't know the mechanism, something would prevent a star from collapsing into a single point and forming a black hole. Because black holes were just too preposterous to be real.
The big blow to this belief came in the late 1930s, when J. Robert Oppenheimer and George Volkoff found that neutron stars also have a maximum mass. Shortly after, Oppenheimer and Hartland Snyder showed that for the heaviest stars, there is nothing left to save them when their fuel runs out. They wrote, "This contraction will continue indefinitely." But Einstein still couldn't believe it. Oppenheimer was saying that stars can collapse indefinitely, but when Einstein looked at the math, he found that time freezes on the horizon, so it seemed like nothing could ever enter, which suggested that either there's something we don't understand, or that black holes can't exist.
But Oppenheimer offered a solution to the problem. He said, to an outside observer, you could never see anything go in, but if you were traveling across the event horizon, you wouldn't notice anything unusual, and you'd go right past it without even knowing it. So how is this possible?
We need a space-time diagram of a black hole. On the left is the singularity at r equals 0. The dotted line at r equals 2m is the event horizon. Since the black hole doesn't move, these lines go straight up in time. Now let's see how ingoing and outgoing light rays travel in this curved geometry. When you're really far away, the future light cones are at the usual 45 degrees. But as you get closer to the horizon, the light cones get narrower and narrower, until right at the event horizon, they're so narrow that they point straight up. And inside the horizon, the light cones tip to the left. But something strange happens with ingoing light rays.
They fall in, but they don't get to r equals 2m. They actually asymptote to that value as time goes to infinity. But they don't end at infinity, right? Mathematically, they are connected and come back in, and they're traveling in this direction. And this bothered a lot of people. This bothered people like Einstein because he looked at these equations and went, well, if nothing can cross this sort of boundary, then how could there be black holes? How could black holes even form?
So what is going on here? Well, what's important to recognize is that this diagram is a projection. It's basically a 2D map of four-dimensional curved space-time.
It's just like projecting the 3D Earth onto a 2D map. When you do that, you always get distortions. There is no perfectly accurate way to map the Earth onto a 2D surface, but different maps can be useful for different purposes. For example, if you want to keep angles and shapes the same, like if you're sailing across the ocean and you need to find your bearings, you can use the Mercator projection. That's the one Google Maps uses. A downside is that it misrepresents sizes. Africa and Greenland look about the same size, but Africa is actually around 14 times larger. The Gall-Peters projection keeps relative sizes accurate, but as a result, angles and shapes are distorted.
In a similar way, we can make different projections of 4D spacetime to study different properties of it. Physical reality doesn't change, but the way the map describes it does.
He had chosen to put a particular coordinate system over space and have a time coordinate. And off you go. It's the most sensible thing to do, right?
People realize that if you choose a different coordinate system by doing a coordinate substitution, then the singularity at the event horizon disappears.
It goes away. That problem goes away. And things can actually cross into the black hole.
What this tells us is that there is no real physical singularity at the event horizon. It just resulted from a poor choice of coordinate system. Another way to visualize what's going on is by describing space as flowing in towards the black hole, like a waterfall. As you get closer, space starts flowing in faster and faster. Photons emitted by the spaceship have to swim against this flow, and this becomes harder and harder the closer you get. Photons emitted just outside the horizon can barely make it out, but it takes longer and longer. At the horizon, space falls in as fast as the photons are swimming. So if the horizon had a finite width, then photons would get stuck here. Photons from everything that ever fell in. But the horizon is infinitely thin, so in reality, photons either eventually escape or fall in. Inside the horizon, space falls faster than the speed of light, and so everything falls into the singularity. So Oppenheimer was right. Someone outside a black hole can never see anything enter, because the last photons they can see will always be from just outside the horizon. But if you yourself go, you will fall right across the event horizon and into the singularity.
Now, you can extend the waterfall model to cover all three spatial dimensions, and that gives you this, a real simulation of space flowing into a static black hole, made by my friend Alessandro from ScienceClick.
That is, like, insane. Like, how would you be able to, like, make a diagram of that?
Yeah. I mean, I like how he does the 3D things. Like, it really helps me understand exactly what he's saying, you know?
Yeah. Like, if you were just listening to this, like, on a podcast without a video, like, you guys are probably, like, if you're not watching the video, you guys are probably just like, duh.
Yeah. Go check out the YouTube channel. It's gonna be called Just Two Guys. I'll post it this weekend.
Oh, yeah. And guys, we are going to try to post once a week, but since we are both doing school and sports, we might, like, have a bit of a flexible schedule.
Yeah.
Oh, and also, sorry about not posting on most of the websites because we had to have something figured out. So pretty much everything but Spotify will not have one of our episodes, but we will add that.
Yeah, we'll get them on there soon.
Yep.
As soon as we can. All right.
Later, we'll use this model to see what it's like falling into a rotating black hole. Now, I've never been sucked into a black hole, but sometimes it feels like it when I'm stuck on the phone with a spam. And so I wanted to go on and even your social.
I'm at the top of my game.
Vital Proteins Collagen Peptides for healthy hair, skin, nails, and joints.
We're not getting free advertising.
Oh, you the Geico Gecko! I filed a claim for my car with the Geico.
Social security number, and then self, but it's a super tedious 62 hours of work. Veritasium to get 60% off. So head over to incogni.com/Veritasium to get started. I want to thank Incogni for sponsoring this part of the video, and now back to space-time maps.
If you take this map and transform it so that incoming and outgoing light rays all travel at 45 degrees like we're used to, then something fascinating happens. The black hole singularity on the left transforms into a curved line at the top. And since the future always points up in this map, it tells us that the singularity is not actually a place in space, instead it's a moment in time. The very last moment in time for anything that enters a black hole. The map we've just created is a Kruskal-Zeckers diagram, but this only represents a
what now diagram?
portion of the universe, the part inside the black hole's event horizon and the part of the universe closest to it. But what we can do is contract the whole universe, the infinite past, infinite distance, and infinite future, and morph it into a single map. It's like using the universe's best fisheye lens. That gives us this Penrose diagram. Again, light rays still always go at 45 degrees, so the future always points up. The infinite past is in the bottom of the diagram, the infinite future at the top, and the sides on the right are infinitely far away. The black hole singularity is now a straight line at the top, a final moment in time. These lines are all at the same distance from the black hole. So the singularity is at r equals 0, the horizon is at r equals 2m, this line is at r equals 4m, and this is infinitely far away. All of these lines are at the same time.
What's great about this map is that it's very easy to see where you can still go and what could have affected you.
For example, when you're here, you've got a lot of freedom. You can enter the black hole or fly off to infinity. And you can see and receive information from this area. But if you go beyond the horizon, your only possible future is to meet the singularity.
Yeah.
I was just gonna say that infinity is like so crazy. Like, how could you, like, is space infinite really? I wonder if, like, there's ever gonna be an end to space.
Yeah.
Like,
well,
if we ever find it out.
That's true. They did discover, like, there's proof that the universe is expanding still, but it's like you said, will it ever stop expanding and stuff?
Mm-hmm.
Also, like, yeah.
Yeah. Also, will.
Veritasium.
Oh my bad. You go.
You go.
All right. I was just gonna say, like, what will happen, like, if the galaxy, like, if our Earth and, like, the galaxy and all of that, what if it, like, just, like, stops existing? Like,
Yeah.
like, that would just be crazy because, like, all we know, all we live, all that stuff would just be gone in an instant. And it's, like, just such a small part of the universe. It's just insane.
Yeah. Also, what I was gonna say, there's another Veritasium video. It explains how different infinities are bigger than others. It's wild.
Yeah. Numbers alone are just crazy.
Yeah, they don't make sense.
Mm-hmm.
All right.
Clarity. You can still, however, see and receive information from the universe. You just can't send any back out. Now, think about being at this point in the map. This is at the event horizon, and now your entire future is within the black hole. But what is the past of this moment? Well, you can draw the past light cone, and it reveals this new region. If you're inside this region, you can send signals to the universe, But no matter where you are in the universe, nothing can ever enter this region because it will never be inside your light cone. So things can come out, but never go in. This is the opposite of a black hole, a white hole.
What color is a white hole?
Ooh. I mean, it's going to be it's not going to have a color, right? It's going to be whatever's being spat out of it. It depends what's in there and gets thrown out. That's what you are going to see. So if it's got light in there, it's got mass in there, it's all going to be ejected. So the white hole kind of picture is the time reverse picture of a black hole. Instead of things falling in, things get expelled outwards. And so whilst a black hole has a membrane, the Schwarzschild horizon, which once you cross, you can't get back out, the white hole has the opposite. If you're inside the event horizon, you have to be ejected. So it kicks you out kind of thing, right? Relativity doesn't tell you which way time flows. There's nothing in there that says that is the future and that is the past. When you're doing your mathematics and you're working out the behavior of objects, you make a choice about which direction is the future. But mathematically, you could have chosen the other way, right? You could have had time point in the opposite direction. Any solution that you find in relativity, mathematically, you can just flip it and get a time reverse solution, and that's also a solution to the equations.
Now, we've been showing things being ejected to the right, but they
Can you
could
pause
just
it
as
real
well
quick?
be ejected to...
All right. Just like that's insane. Like that's literally time travel if you think about it. Like
Yeah.
white holes.
Yeah. It's crazy.
It's just
Like,
insane.
He said, like, you have to go faster than light to go out of your light cone. So theoretically, you could go into the white hole. You just have to literally go faster than light, which that's crazy.
Yeah. Also, like, it's crazy how far light can travel. Like, if you use a telescope, like one of those huge ones, it's like insane how far it can reach.
Yeah. All right. Well, I have to go to bed right now, so we can do part 2.
All right. Well, thanks everyone for watching. We will do a part 2, and yeah.
All right. Thank you.
All right. Thanks.